Okay, we're answering a homework question, and the question says, from our book, given the following reduction half reactions, and it lists 4 half reactions, ferric going to ferrous, dithionate going to sulfuric acid, dinitrogen oxide going to nitrogen gas, and the vanadiol, I think it's called VO2+, I'm not sure what the name of that ion is, going to VO2 plus, and they give the voltage for the standard reduction potentials for each one. And the first question says, write a balanced chemical equation for the oxidation of ferrous by dithionate. And then later on asks for part B, calculate delta G naught for each reaction at 298 Kelvin, and C, calculate the equilibrium constant K for each reaction at 298 Kelvin. There are two equations that are needed to solve this. The first is this one, delta G is equal to negative NFE, and delta G equals negative RT ln K. But first we'll balance the electrochemical reaction. These are 2 half reactions they give us, and I've already taken the liberty of flipping this one. Or sorry, I think I may have flipped the second one. Let me see. No, I flipped the first one. This is the one I put backwards. So the ferrous is being oxidized to ferric. Another electron is being taken away from it. And it's being oxidized by the dithionate anion. We have to multiply this whole reaction by 2 because only 1 electron is here, whereas 2 electrons are there. So the reduction is furnishing 2 electrons and the oxidation is giving up 1. So we're going to multiply the oxidation by 2. The voltage stays the same. You don't multiply the voltage. So the standard voltage for this reaction is negative 0.17, which would signify to us that the reaction tends to go the other way. So if we balance it, we see that since everything is multiplied by 2, we get 2 ferrous, 2 ferric, and 2 electrons. And the 2 electrons are already cancelled. I didn't write them here. And then the dithionate we write as is. Everything is there. So everything that appears on the left appears here. Everything that appears on the right appears there, except if it cancels. We add the voltages, that's why we get negative 0.17. In the next phase of the question, they ask us to find the free energy for the reaction. 2 electrons are exchanged, that's what this N symbolizes. The F symbolizes Faraday's constant, which is the charge on 1 mole of electrons, so it's 96,000 coulombs per mole of electrons. And E symbolizes the voltage of the whole cell. The overall voltage is negative 0.17. The units are volts, but I took the liberty of writing them as joules per coulomb, because the volts is a unit built up of 2 other units. When you write it that way, then you can see how moles cancel here, coulombs cancel there, and you're only left with an answer in joules, and that's the free energy. So the free energy is a positive quantity. When you get a positive free energy, it means energy has to be put into the reaction to make it go, which stands to reason because the voltage is negative. When you get a negative free energy, on the other hand, it means the reaction has extra energy left over to do work. So the final answer for the free energy for this reaction is positive 3.3 times 10 to the 4 joules. We then continue the calculation to find out the value of K, the equilibrium constant, by plugging into delta G is equal to negative RT ln K, where R is the gas constant, T is the absolute temperature, that is the temperature in Kelvin. To find the Kelvin temperature, you add 273.15 to the Celsius temperature. And then, having plugged in the values, you get the value of ln K. To find K, take the inverse ln, which means you raise e to the power of whatever this number is. So we find out that K is negative, is 1.8 times 10 to the minus 6, which means the equilibrium is shifted far to the left towards the reactants, and that makes sense because this reaction favors the reactants. In fact, these should be the products, and so all of that fits together. In the second problem, we had the ferrous ion being oxidized by dinitrogen monoxide. The voltages here are listed, the standard voltages are listed. Now, if we were to write this reaction as it tends to happen, we would flip both of these. But that's not what they're asking us in the question. What they're asking us in the question is to find out what the value of the free energy is and what the value of the equilibrium constant is for this reaction. So that's what we're going to do. We're going to leave them as they're presented, balance them, which means that we need to multiply the first one by 2. And that allows for the electrons to be canceled. We get this as your net reaction and a negative voltage of 2.54. We again plug that into the equation delta G is equal to negative NFE. 2 electrons are being exchanged. Here's Faraday's constant. Here's the voltage of the reaction expressed in joules per coulomb, so that we can see how they all cancel out for the units, giving you an answer in joules. And the final answer is that you have a free energy of 4.9 times 10 to the 5 joules, which means the reaction, again, needs to have energy pumped into it to go. And it tends to go the other way. You flip the reaction, that's where you're going to get free energy. We again rearrange the delta G is equal to negative RT log K to find the value of the equilibrium constant, or at least the natural log of the equilibrium constant. And we find out that K is equal to 1.2 times 10 to the minus 86, which means it's shifted very far to the left. This reaction is highly unfavorable as written.